Hello, welcome to week 3 of COMP9417, the tutorials. Today we'll be talking about classification. We'll be talking about how it's different to your regression. We'll be going through some examples of some classifiers. For example, here we've got your basic linear classifier. We'll talk possibly a bit about the Bayes, I suppose a probabilistic Bayes classifier, a Bayesian classifier. We'll talk about cross-validation. I know I spoke about it last tutorial, but I'll give it a do over here. Given it's in the lecture slides. Talk a bit about distances. I'll talk about nearest centroid classifiers, such as these ones, but then also the k nearest neighbor classifiers as well. Okay, let's get started. So, in a nutshell, classification versus regression. Now, your classification is a task when your target is categorical, or it just has so many unique levels, right? Maybe a finite number of unique levels. So, say for example, here this is a classification exercise. You're given some data about emails and you want to work out, is it spam or is it not? So there's two levels. There are two categories. This will be a binary classification exercise because it's yes no, a true false, 0 1. Right? It could also be a variety of other things. So another example given in the lectures was about whether a customer would be a good or a profitable or not profitable customer. So here you have this is observation 1, observation 2, observation 3. This is the targets, and these are the features. And you feed into the algorithm, and you want to predict whether it's going to be a good or bad customer. And you can imagine, here, the more user credit you had, possibly the better a customer they can be. They've been with you so many years. It could be that the more money they own, the better a customer they are. It could be that the more money they're borrowing from you, the better customer they are. But maybe there'll be some interaction between these two, right? So a high loan balance is good because you can earn more interest off the credit card or mortgage, but only if they can cover it, right? So it might not be as complicated as that, but I'm just trying to give you a bit of a flavor as to why these might be predictive. And then this is your classification exercise here. Could be a variety of different other things. You could have a model of say an insurance context. Whether a given policyholder will claim or not, given their policyholder attributes. So you could have a model which will predict, and we do have these models that predict. Someone who is say 25. Has had the license for like 6 years, lives in let's say Maroubra, drives a Toyota Camry, which is from, let's say, year of make 2000. Is a male, and all those features will be fed into a variety of models. Could be a whole bunch. Could be linear models. Could be an extension of that generalized linear model. Could be like a gradient boosting machine, and those are models which are quite common in, I guess, insurance pricing. The gradient boosting machine we'll talk about in later lectures. So in that case, it could be considered a classification exercise in that whether the policyholder claims or not in a given year. Now, I stress that in practice, we might not go down that route because it doesn't allow for multiple claims within a given year. We might do something a little different. But just for simplicity's sake, you could think of it as claim or no claim, right? In contrast, and there could be other examples of classification exercises. Say for example, possibly, I'm pretty sure Google has a whole bunch of click-through models. So Google, not the spying you, but they track a whole bunch of data from you. They look at your IP address, they'll look at the kind of browsers, your browsing history, and if you're logged into your Gmail, it's constantly tracking your search history, YouTube, this and that. Again, I'm not trying to sound paranoid, but I'm just illustrating to you the kind of features that Google might have available to you, and then they might have a form of prediction of view of you. So let's say myself, someone like myself, they'll look at the attributes and my search history, what YouTube videos are like, and they'll maybe have some sort of algorithm which looks at the chance of me clicking through, clicking through like this into the website. Now why would Google care about this? Google care about this? Well, Google makes money, ad revenue. That's a big part of their business model, and in terms of ad revenue, you need to understanding who's going to click on your ads is important in terms of optimizing the ads, tailoring the ads, giving the right ads to the right people. You want to give car ads to people who like cars. You want to give, say, clothing ads for maybe female clothing ads for people who want female clothing, etc., etc. So this is important, and also from a sales and marketing point of view, Google will probably want to show, hey, look, if you pay us so X amount of money to put your result up the top, here's an indication of the amount of clicks you might get, or amount of traffic you might get to your website. Okay, so that's another example of your classification. Right. What else? So one quite basic classification algorithm is what's called your basic linear classifier. Now, this is not to be confused with your linear regression, nor is it to be confused with your linear models, right? So maybe I'll just flesh it out a little here. Let me go do it here. So linear regression, linear models, and then you have your linear, or maybe I'll call it the linear classifier. And then you have regression. So these share a lot of words amongst them. They're all slightly different, right? So this is a line of best fit used for regression, as opposed to to classification. Put this here. I'm gonna move this guy here. Move this guy here. Right, linear models. It's largely synonymous with linear regression. Can't spell. Your linear classifier, I'm about to go through here. So this is not to be confused with linear regression. It is a line of best fit to divide, I suppose, categorical data. I'm going to say line or hyperplane or plane. A best fit to divide categorical data. Regression in general is, I suppose, a machine learning task where the target is not categorical. E.g., like maybe it's the real. I don't know what I think it's like. E.g., the real number line, maybe positive integers, etc., etc. Dollars, etc., etc. So not to be confused with those guys. Okay, cool. So I'll talk about the linear classifier here. Then, if in that case, I'm just going to make a little bit more room for myself. Okay. Right, so here in this example, say you have a bunch of data. You have, these are fish. These are two species of fish. It's how light they are in terms of perhaps the color of the scales. And this would be the width of the fish, right? And you can see a clear pattern here, right? So these blue guys here, it's sea bass. It's one species of fish, and these are, I guess, I want to say salmon-colored guys. These salmon-colored dot points are salmon, and so you can imagine, right? If you wanted to create an algorithm and say there's like a let's say there's a new data point and it's unknown. I'm gonna make it green. Unknown. You don't know what it is. This is a new data point, and it's got certain features. It could be that maybe the lightness. How do you measure lightness? I want to say something to do with luminosity, lumens, but I don't think that's quite right. But look, some arbitrary, let's just call it some arbitrary unit of brightness or lightness. Let's call it like, maybe let's call it like 5, right? Okay. And then in terms of width, that is easier. I'm just going to call it, I'll call it 30 centimeters. Let's go SI units. I'll call it 0.3. This is in meters, let's say. And this is in lightness, lightness units, we'll call it. I'm not a physicist. I don't really know too much about that, but we'll call it that. So then, basically, you want to construct an algorithm such that if you have a new data point, such as this green guy here, it can tell me, what the algorithm thinks it is going to be salmon or sea bass. Now, this is obviously a quite simple example, so you and I would probably say it's salmon. I mean, we don't know for sure. Maybe if we had more data points, sea bass, might have some. It might not be linear, and that's the point here. This linear classifier uses, I suppose, straight lines. So it uses straight lines slash planes slash hyperplanes. Hence the name linear classifier, right? So I mean, you could argue that with more data points, and we don't know, it is possible that maybe maybe it looks something more like this. Why should nature be linearly split up like this? There's not really any reason, right? And if actually the true separating, I suppose, curve looks like this, then this should actually be perhaps sea bass. Anyways, given this data, this is probably the best we can do, and I wouldn't. And again, with the concept of Occam's razor or parsimony, you wouldn't prefer this sort of weird model. You'd probably want this, and there's other things as well which we'll talk about later. When we talk about support vector machines, as to why this could be considered, the best linear classifier, right? So how does this work? So effectively, you construct a straight line or a plane or a hyperplane, right? So just think, back to high school maths or whatever. Y equals to mx plus b, but in this case, it's not quite that. This would be, say, you can think of it as x2 equals to mx plus. Actually, I'm gonna use a bit of notation here. Or I'm using the same notation here. We'll call it beta. They're using a, aren't they? I'll call it a then. ax1 plus c, and the c there is the what we'll often call the bias term, but we'll think about that in a bit. Yeah. So this guy here is essentially your straight line equation that hopefully you're familiar with, just rearranged, right? Rearranged, okay. So then you might rearrange this, and then you might have, like, say, well, you could convert it into, you could put a coefficient in front of there, I suppose, but in this case it's I suppose it's 1 because we've defined it to be, we've set this as a subject, but you can maybe I shouldn't have used a, I should perhaps use a on b, and this might be c on b. Oops. Yes, here we go. So maybe something more like this, and then the a on b is the gradient, right? And so then, of course, actually perhaps I should make this negative, yeah. I'm just playing around with the algebra here, just to make it look like this. I'm just trying to draw a link between this form, the general form, and your y equals mx plus b form. So then hopefully you can see, if you rearrange this guy here, oops, you'd have something. Well, you'd have this. You rearrange this, and you'd have that. Multiply by b, move everything around. Okay, cool. But then here's the thing. So once you have, oh no, once you have, let me just grab these guys here. Cool. So yeah. So once you have this guy here, okay. Once we're comfortable with this guy here, we then need to come up with some sort of prediction, right? So what is our y hat? And again, hat means prediction. So how do we use this to predict? Okay. Um, so you might do something like this, if this, if say ax1 plus bx2 plus c greater than let's say 0, then we'll go say y. Our prediction is that it's of the positive class, we'll say. And then we could say else hats equals -1, right? Yeah, I mean, there is a edge case of sorts in the middle where it's 0. That, I mean, you could set it to either or. You could have it so that it is greater or equal here, and then else that, or you could just have this. I don't think it really matters either or. Cool. So this is your basic linear classifier. Let me pop back to the lecture slides and see what else is interesting here. Yeah, so they have a slightly different example here, but it's the same kind of idea, right? You have your observations, these are your dots, and then your x1, x2, and then it's plotted here, and then you want to find your best separating hyperplane or line. Okay, now yeah. So this one here, yeah, this is basically the same as what we were talking about before. This is the dot product with the weights expanded out. So if you dot these out, you'd have W0, you'd have W1x1 plus W2x2 up to however many predictors you have, and then your bias term. So it's the same as what I had before there, right? This is an interesting result, right? The weights and it's sort of the gradient, right? So the gradient of this guy here is perpendicular, right? So this guy here, W, is just all the coefficients in front of the x. But it is interesting result. The gradient is vector is perpendicular. We will touch on this a little more, this whole concept, because the support vector machine builds upon this. Yeah, Bayesian classifier. So let me jump back to my slides, and I'll talk a bit about your Bayesian classifiers. Now I hope you're all somewhat familiar with Bayes' theorem or Bayes' rule, right? If not, I'll give you a brief overview, and I suggest looking it up yourself. But this is essentially the theorem, right? The probability of something happening given a condition effectively allows you to reverse the condition in your probability statement by doing something like this, right? I'm not going to go through the proof. If you're interested, you can Google it yourself. But it is useful in the context of classification. We can use this Bayes' theorem in order to generate a probabilistic classifier, right? So this is an example which comes up time and time again. It is the maybe not misnomer, but when people hear about, say, the accuracy or the sensitivity and specificity of a given let's say medical diagnostic test, they assume that if it comes up positive, they probably have it, or that they assume that if the test comes up positive, the probability of them having that, say, cancer is that accuracy or that sensitivity or this value here, the probability of it coming up positive given it's cancer. The the reason that it's not quite what it seems is because most people don't have cancer, right? So if you look at the total number of, I guess, positive, I guess, test results, because so few people have cancer, you're going to get a lot of false positives, right? You're going to have a lot of times that it comes out positive, even though you don't actually have cancer, right? So look, you know, and so this example here is running you through your Bayes theorem. So in this case, A would be, say, your cancer, and B would be here this is just indicating a positive test result. Here it's indicating a negative test result, right? So you can use this. Here we go. You can use Bayes' rule to work out, okay, and what is it that we actually care about? We care about the probability of having cancer given it's positive. So we basically want to flip this conditional probability around. How we do that is using Bayes' theorem. You can see here it lets you switch the conditional probability around. Here it is in practice. Sorry. Can I get rid of this? Yes, here it is in practice. We want to flip it around. Okay, so you follow this, and the reason why the denominator isn't there is because the probability of the conditional, which is the probability of cancer given positive, this one doesn't change. This one is the same for both of these, because we essentially want to work out what is higher. The probability of me having cancer if the test is positive versus the probability of me not having cancer given the test is negative. Now, to find this out, right? So in this case, this would be, I suppose, the B, right? B given A, isn't it? Probability of, so that's A, isn't it? So cancer is A in this case. So the probability of cancer given positive. Now, for both of these, the denominator is a probability of having a positive test case. The denominator is the same in both of these, right? Because the A in the top one, maybe I'll flesh it out so I can sort of sub it in. So in the first example, A is equal to cancer. I'm talking about this formula here, and then the conditional is equal to as a positive test. Now in the second example, that's this one. Now in the second example here, it's probably not cancer given positive. The denominator is the same, so you can calculate this, but it's not necessary. Just ignore this maximum A posterior. I can't even say it. Find the maximum A posteriori hypothesis. I'm pretty sure I'm not saying that right. Essentially, it's saying you want to find what's more likely. Do you have cancer or not cancer given it's positive? And these are proportional. This will just scale it so the sum of them is equal to 1. The law of total probability demands that the sum of these. I suppose the sum of these it's equal to 1, right? Okay. So I'll let you run through this example in your own time, but let me talk about how you can use Bayes' theorem in the form of a Bayesian classifier, right? Okay, so this is Bayes' theorem. Now we can sub in Bayes' theorem with the things that we care about for a classification exercise. Now, y is the target. So for binary classification, it could be something like it could be something like let's call it why did that come out? Let's call it -1 + 1. So it's either or, right? This is a binary classification. It could be, it may not have to be binary. In fact, this you can apply to a regression example, although you'd have to replace the probability. You'd have to use a probability distribution of some sorts as opposed to a discrete. But that's fine. So we are basically replacing the A and B with our classification task, which which your y and your x will be your features. Again, this is the vector of features for that given observation. So just plug it in, you should see it. So how do we use it here, right? So in this case, what we're trying to find is the probability of y, and it could be, and the y is, say, salmon. Maybe the probability of salmon, given the features, right? Now, this guy here is essentially this guy here. So this probability of, this is x given y times probability of y. X given y times probability of y. That's what this one is doing here, and the same down there. But how do we calculate this, right? So probability, I mean, hopefully you can follow along, what I'm subbing into where. But how do we find the probability of it, being 70 centimeters given salmon? We can estimate it, right? So this is an estimator. This is an estimate because we don't know the true probability. But this is the best we can do. So we look at what's called the empirical frequencies. What I suppose the probability that you see in the data, the empirical frequency. Okay. So what is the probability of, say, 70 centimeters given it's salmon, right? So here is salmon, and this adds up to 1. The probability of 70 centimeters, it's 0.4. So we put 0.4. Maybe I'll doodle a bit more to make things a bit easier. So we put the 0.4 into there, right? So then we have the probability of salmon. Now, this is actually given. So it's not in this table, but this is something you were told earlier. So the probability of salmon and sea bass, right? So what this is I guess the empirical frequencies of seeing each class in like the total data set, right? Now, what does this mean? And this is P, but we're going to use an estimate, right? So for example, like, if in your data set, say 30% of all fish were salmon and 70% were sea bass, then you do something like the following there, right? Okay. So what you do then is you'd multiply it out, and then you'd find out which one is higher, and then that would be your, I suppose, your selection as to what is your predicted class. In this case, we'll go with sea bass because of the evidence that we've seen. Okay. If you want to note this doesn't add up to 100% because we haven't divided by this. If we divide it by that, then it would scale to 100%. But here we're just trying to maximize, so it's not entirely necessary. Okay. Next, let's move along to cross-validation. Now, I touched upon this, and I touched upon this last week, but I'll go over it again quickly here. Yeah, I'll go over it again quickly here. So you might recall there were several different ways to go about splitting your training and test data. You could even have, I suppose, your validation data set, right? Cross-validation can be applied to your training. Again, it can be applied to at your training level, but you can also use it at the validation level. Can you? Yeah. Do we want to use at the validation level? Training for sure. We definitely want that. No, sorry, I take that back. You probably want to use the bigger training data set, and if you have validation, you might use it to test out some other things, but you do maybe your cross validation here to test out a bunch of things, and if you want to do more tests, then you can use this data set here. So what it essentially entails is, and I just realized what these dots were. It's the classes, the binary classification, right? So in this case, we are doing k-fold cross validation, and here we're doing 7 folds. This here is 7 folds. What you do is you subset your training data set, and this entire block here is your training data set. Your training data set, and you will train on, I suppose, within each of these, you'll train on 6/7 of it. Oh, I should probably use a different color so we can see. I will use purple. So you'll train on, say, 6/7, in this case, 6/7 of the data, and then you'll calculate, I suppose, I guess for what a cross validation, I guess maybe score for that fold. Okay. Then, and which is on, say, 1/7 of the data. You repeat this exercise, cycling through all your partitions of the data. At the end of this exercise, then you will average it out. Okay. Right. Yeah, so again, I went through this in significantly more detail than last week's tutorial. At the end of that, so there was a question. Sorry, no, I didn't. I was in the question time, wasn't it? So maybe I'll pull this up just in case you guys weren't there. Okay, so, ooh. Okay. Right. So here, let's have an example. Let's call it 4-fold cross-validation. Here's my data set, and I fit it 4 times, right? First time, I fit it on the first 3/4 of the training data set, and then I calculate the cross-validation score here, 75%, and then I cycle across. Here we go. Your CV score is just the average of them. You can also calculate something cool, which is a standard deviation of them, and all else equal, you want less of this. It's an indicator of the variance of the model. And as you know from a bias variance decomposition, that is one of the sources of error and misfit in a model. Okay, cool. Now this begs the error. This begs the question: what is classification error? What is error? In root mean square land, it was fairly straightforward. It was quite easy. I think it was a lot easier to understand. You know. I don't know if it was easier, but at least in the regression land, you'd use something like, root mean square error. That was a common one we had, and that was effectively just, you subtract off the differences between your actual and your predicted. You square it all, and then you take the average, right? In classification, there's a whole bunch of them. There is the easiest one to probably wrap our heads around, and probably the easiest to understand, is accuracy. So yeah, this one, it's simply, it's simply, it's just the number of correctly classified observations divided by number of total obs. Very straightforward, nice and simple. This does come with a bunch of problems though. So the weakness here is with what's called imbalanced classes. So an imbalanced class is like if you have, say, like +1 class makes up maybe 99% of the data, and let's say -1 class makes up, say, 0% of the data, not 1% of the data. Let me illustrate to you why this is not great using accuracy, right? Now, when you use accuracy and it's highly imbalanced, you are, I guess, you tend to bias using accuracy to choose a model in imbalanced class situation. You'll tend to bias your prediction towards the majority class, right? Let me give you a bit of a silly illustrative example as to why this might happen. Right? So let's say I have a model which maybe detects whether someone is going to be let's say, I'll be a bit morbid, I apologize, is going to pass away tomorrow, okay? And what if I told you, and let's just also say that, you know, in reality, this chance is maybe the next pass away in the next, say, year, right? In reality, the chances, and again, this depends on age, but let's just say it doesn't look at. Oh, I mean, because it might look at age in the future, but let's just ignore that and. No, actually, I'll go for a similar model. Well, let's get a model which detects whether someone is a plane hijacker. I apologize for the morbidity. Yeah, and let's say in reality, maybe like 0. Like how many people, how many customers on a plane are really, it's tiny. This is probably overestimates anything. My sense of scale gets a bit warped when it gets this small. I mean, it's probably like 1 in a million, like less than that, right? So it's at 2, 4, 5. Yeah, that's 1 in a million. So I'm just gonna call it that. Okay, let's say it's this. It's maybe more, but let's just call it that, right? Now, what if I told you I have a model which is 99 point. Actually, so that's okay with the percentage. Which is 99.12345. Is that right? 1, 2, 3, 4, 5, 6. Is 99 has accuracy? Has this much accuracy? You'd be like, wow, that's a fantastic model, isn't that? That's great. But what if I told you my model was this? It's a constant. It just constantly predicts everyone is not a hijacker. You can probably see some problems there. It's a bit of a silly example, but what I'm trying to illustrate to you is accuracy in itself, right? It only looks at because accuracy, right? It looks at total observations and the number of correctly classified ones. Like if in your total observations, right, most of these people are not plane hijackers, the classifier which is good for that one will dominate, right? And this is a silly example, and this is highlighting a weakness of your accuracy metric. Now, there are other classification metrics kicking around as well. You know, there's a log loss. There is the Gini coefficient. There are a variety of other ones. The F1 score. There's a lot. But I think you know, the Gini coefficient as well as accuracy are quite common. You might drill in a bit into you know, sensitivity and specificity, which breaks up the accuracy into, you know, something more granular, and it might give you a bit more of a flavor as to what you care about. Depending on your examples and your usage, you might care more about certain things than other things. Let me flesh this out a little bit, right? Now, along here, right, I hope you can appreciate that accuracy is a bit of it's a blunt force weapon in a ways. So here, everything here, maybe I'll go green. These are all correctly classified, so they would go here. On the flip side, these are well, actually, they're both good. These are incorrectly classified, and they'll go here. But also the green guy would land here as well. Now, this is a bit not granular. It looks at everything at once, and there are good this is called a confusion matrix, by the way. There are good confusion matrix. Now, there are good reasons why there are applications where you might prefer one or the other. Like, I mean, different algorithms might have different levels of true positive, false negative, etc., etc. Now, I pose an example to you. Let's say this is cancer diagnosis. Possibly, I would argue that the most important thing here is true positive, because like we want to catch all possible cancers. We want to catch all possible cancers, right? Now, this may come at a trade-off of, say, more false positives, but maybe we're okay with this because it is pretty catastrophic to have a false negative where they say you're negative for cancer, but you actually do have cancer, right? There are other examples where you might care about having too many false positives. You want to minimize you want to minimize the number of false positives, right? So you'll minimize the number of false positives. What's a good example? Yeah, so say there's a actually no, I think credit card fraud would probably fall into here as well. Yeah, also credit card fraud. Maybe you're okay with some false positives, but you really want to make sure you got a high true positive rate. You want to capture all the actual fraudulent activity. Struggling to think of more examples, but I'm just going to leave it at that. So I'm going to leave it at that. So these two, I don't know that it's in this week's lecture slides. I could be mistaken, but I'm not going to cover it because it's not in this week's lecture slides. Feel free to give this a squiz in your own time. Now, cross-validation. Yep, good. Okay, let's move on to a bit about your distances, right? There's a bunch of models here which rely on distance. There's the k nearest neighbors. Nearest, you need some definition of what is near and what is far. In other words, distance. There's a few things about distance metrics properties of them, but I mean, in a nutshell, this is the general form, and I hope this is somewhat familiar to you, right? If it isn't, just sub in p is equal to 2. If you do that, it is literally the Euclidean or normal distance that we are used to. So if you sub in p is equal to 2, you'd have your first feature, first dimension minus first dimension are your two things. Your second dimension minus second dimension are your two things. And you square it and you take the square root. Okay? Now, certain ones have different names, and some are more important than the others. I would argue that Euclidean and Manhattan are the most are two of the most common, and in particular Euclidean is the most common distance metric. You should be quite familiar with that. So have a look at those. There's some properties of your distance metrics. Okay. So now that we have a distance metric in tow, now that we have a little bit of a handle on it, I want to talk a bit about your nearest centroid medoid classifier. Now, let me just have a quick check to see if the notation is consistent. I think it is. Did they not cover nearest? They don't cover centroid, do they? Yeah, I know they do. They removed the formula. Okay. That's all right. I can still explain it. So your nearest centroid classifier, I mean, you could ignore this formula if you want. It's a little, maybe it will confuse you a little. Let me just explain what it does. Now what you do is, for your nearest centroid, you're going to basically for each class, you want to, I guess, calculate the sorry, he's talking about coronavirus, in case you're thinking it's something odd. And that's my mate, it's not something sus. Yeah. For each class, you calculate the centroid or the medoid, right? Then what you do is, in order to classify, effectively going to find the nearest centroid or medoid. And that becomes your, then the nearest centroid medoid is the predicted class, right? So that might beg the question, what is a centroid, right? So the centroid, effectively what you do, okay, so this one, what is this? That's not the medoid. Okay, so this is how you calculate one dimension of each centroid. So what you can think of it as doing is you effectively average out the values for everything in that class. Average out the values for everything in that. So the centroid is going to look something like this. Maybe I'll just draw it out. So I'm going to denote it mu. I don't know. I'm just going to denote it mu. And let's say we have, we have 2 dimensions. This is your x1. This is your x2. Now, your medoid, let's say, and this is, let's say, for the actually, so I'm just struggling to work out how I want to notate it, because I don't want to necessarily just put something down here which is different. Okay, he uses a super. Okay, good. Okay, good. No, we're good. Cool. So let's say the medoid, I'm going to say the blue class. I'll just call it blue. This orange, right? Effectively, what you do is, right, you take the, I guess, the average of all the x1. So you take the average of all, I guess, of all the x1, for, I guess, the blue data points. Okay. And then what you do is you repeat this exercise, but for the orange, right? I'm just going to call it, orange. Sorry. No. I did that wrong, didn't I? Then you repeat this exercise for the second dimension, number 2. So you average out all, so you go here, say for example, you look at all the x values, you take the average, and that's this guy here. Perhaps I should give that a bit of a different color. It's also a bit too thick, isn't it? So you get all these are all blue. You take the average, and that feeds into here. And then you take, let's say, the green, and it's this, and it's for all the points, right? You get the idea, I hope. And then that feeds into here, and that's your medoid, that's your centroid, right? Okay. Now, in order to find the medoid, right? It's a similar thing, but with a medoid, instead of averaging, you take the median. Okay, simple as that. Cool. How am I doing for time? Okay, I should move along to the Jupyter Notebook in a little bit. The next one I'll talk about is your k-nearest neighbor. This is quite a simple classifier. Basically, all you do is, you say this is your data set, and I'm going to use purple. and this is your feature 1, and this is your feature 2, right? Now you use your distance, you use your distance metric for all of this, right? And let's say you have an unknown data point, the green guy here. Now what you do is you calculate the distance from the green guy to every single other point. What's the distance to here? What's this to here, to here, to here, to here, to here, etc., etc. Excuse me. You calculate that distance, right? And then what you do after that is, depending on the k, right, depending on the number of nearest neighbors, you will then find the colors. You will then find, yeah, that'll do. You'll then find, say for example, it's k is equal to 3 nearest neighbors. You'll then find the 3 closest observations, right? At which case, your classification will be the most popular. So there's two, I guess, red guys here. So we'll call it class B. So when you use k nearest neighbors for regression and classification, it's one of a few things. So we're talking about most popular class, and we're talking about on this side typically be the average of, say, the 3 nearest neighbors, right? So in this case, let's say we're doing a regression exercise, right? I'm just going to create some dummy data. I am also running out of space. What is a color and colors? I'll use this. Okay, so let's just say, for argument's sake, this is regression, and this guy here is 3. Did I not change color? Let's just say, for argument's sake, this guy here is 3. This guy here is 4. This guy here is 5. Now, with 3 k nearest neighbors of k is equal to 3, the 3 nearest neighbors of these guys, you take the average, and then the y hat would just be your 3, because the average of these it's 3. Okay, cool. Let's shuffle along over to the Jupyter notebook without further ado. Okay, what can I say here? There's a lot to say. Let me zoom in a touch. Okay, one thing to be mindful of, I must say, or considerations with your k nearest neighbors, is that it's distance based, which comes with a few considerations. I should probably say. So KNN, it's distance based, which means that it's sensitive to the scale of the features, right? So you can imagine, right, if there is a feature that's measured, let's say, in millimeters versus a feature that is measured in kilometers, the KNN will strongly bias towards millimeters because the scale is so much higher. And when you calculate distance, it's just going to be like, this could be like in the thousands versus this could be like point something, right? That's something to keep in mind. It is also prone to what we call the curse of dimensionality, which I'll quickly talk about here, and then we'll go back to the Jupyter notebook. What is the curse of dimensionality? Now, there's 2 ways to understand it. There's a mathematical result which shows that as the number of features increases, the distance from one observation to another just tends to 0. It just gets to 0 very, very quickly, and then everything becomes sorry, not 0, because it blasts to infinity. Sorry, it blows up to infinity. So everything becomes very far away from each other. Now, I like to think of it this way. I think this way here, which to me is easier to understand. Let's say here we have some arbitrary set of data, and let's just say we have 1,000. Let's call it 54. let's call it your 54 data points, right? Now, if you have one feature, right, you could argue that each one of these might have, say, 18. It depends on how you cut it, right? But let's say you have some sort of decision tree, and you split your data, right, into three nodes or leaf nodes, perhaps, right? Each one of these, again, depending how it's split, let's say it's 18 for argument's sake, right? Okay, that's some amount of data. Okay, cool. Now, moving along to here. Now, the splits of all this data is going to be much worse. You're going to have 6, let's say, in each square, right? And why is this? Because you have another feature, right? If you want to look at all, I guess, the unique combinations of, let's say, what are all the observations where x1 is looks like this, x2 looks like this, right? It increases exponentially, right? The number of these boxes or partitions you have increases exponentially depending on the number of variables. So you can see it here, right? So for one dimension, you need 3 parts, let's say. For 2 dimensions, it's 9. For 3 dimensions, it's to the power of 3. So you can see it's blowing. It is indeed blowing up here, right? So let's just make the assumption that you need your 3 parts, right? So effectively it's this guy here, and so and let's say I have a data set of, let's call it 1,000, right? And these are the number of maybe partitions. Why a partition? Because, as I say, so I mean, the way all these algorithms work, especially k-nearest neighbors, it looks at the ones which are, say, for example, has that specific combination of x1 is x2 is like this, or x1 and x2 is like that. So that's what this looks like. And then what you'll find is, say, and then this is observations per partition. So you'd have something in the order of this guy here. Okay, so I hope you can kind of see what's happening here. Like, two things are happening here. One, this looks kind of there's some exponential growth happening here. There's some exponential growth happening here. Hope I can demonstrate to you. Yep. Okay. And the other thing to keep in mind is that the observations. Let's actually say let's have more data. The observations per partition, just like you add a few more features, man, it is just like by the time you have 12 features, every partition might only have like 2 observations, which is just, imagine the variance on that, right? Imagine the variance on that estimate. It might not be very good. And this is, I think, another way to understand it. In the Jupyter notebook, they show it to you. They just show it to you. They don't prove it necessarily. They just have a data set and they demonstrate. That's what they demonstrate to you, right? So the problem with high dimensionality data with your distance-based machine learning algorithms is you run into what's called the curse of dimensionality. Okay, so this is what's showing here. Now this code isn't too important. I think more important is what it's trying to show you, right? It's showing that basically, curse of dimensionality says that as the number of dimensions increases, like everything just becomes far away, and everything becomes everything becomes far away, and everything becomes harder and harder to interpret. I feel like I had a actually let me open up something else. I feel like I had another Jupyter notebook with a few more notes in it. No, where is it? Where did I put it? It's not here. I don't even know. Where is it? Here it is. Okay. I think I had something from last semester. gives me a bit more flavor. I thought that was one which I did some things on. There's lab 4. What am I doing? Lab 2. Lab 2. Oh no, it's right here, isn't it? Sorry, let me just try this again. Let's do this. Week 2. Week 3. No, but that's a question, isn't it? What's the answers? Did I write? Okay, look, it's fine. I've got enough here, I think. Cool. Yeah, so the way to interpret it, what is this? This is a ratio of the minimum maximum. Notice how it's converging to 1 quite quickly. What this is saying is, as you increase the number of dimensions, everything kind of just becomes same. The distance you have is just everywhere looks the same. And actually, what you can do to help visualize this effect is, the distribution of the actual distances. If you look at the distribution, you'll find that as you have higher and higher dimensionality, everything just becomes super far away, you know? So even though here, what this is showing is that all the distances are becoming the same, we did another graph to show that the average distance between all the other points is also increasing. Now, the next thing we'll do here is we'll implement nearest neighbor from scratch. There's a bunch of interesting things here. And as I say, make sure you're up to scratch with your Jupyter notebooks, your NumPy, your scikit-learn, your pandas, right? We start off by creating a bit of data, there is it. We start by creating a bit of data, and like, you don't need to worry too much about this, but the way this is generated using a multivariate normal. So I mean, I don't think this is directly in the course, but it's just for interest, as how it's generated. So these are 2 multivariate normals with some level of covariance between the 2. But that isn't the important thing about this. The important thing about this is we want to use this data set to generate a model. So we have feature 1, feature 2, etc., etc. Okay, so this is they've generated the data, using your bivariate normal. So here's your mean vector, your covariance matrix, and then you do it again. Then you create the random multivariate normals and the bivariate normals, right? And then you plot it. And here it's basically mushing the data from before. These dots are being put into in tabular form, into pandas, I suppose, data set. So yeah, we the next thing we do is we need to implement it, right? And one of the pieces in it, you can. There are plenty of pre-built distance functions in NumPy and SciPy, and what have you, but it's interesting to make it ourselves so we have a better grasp on what's happening, especially given that they cover the various Minkowski distances of various norms, L1, L2, L whatever, right? So this is just your L2 distance. You return that. And how does k nearest neighbors work? So this is we create a k nearest neighbors, I suppose, algorithm, and it takes in your training data, which would be these dot points, and your labels, your class labels. So this should just be like one column of just say it's blue, orange, blue, orange, whatever they are, right? This is like a new unseen data point. And this is the number of neighbors. So the number of neighbors, here's 3, there is 12, etc., etc. Now what you do is you go through each of the training data points, and you want to calculate the distance between each observation and that new unseen data point. The idea being is you eventually want to work out a list, or maybe an array of all the closest, like say in this case, k is equal to 7 many data points. Now, once you loop across and append, so now you have a list. This list called vals gives you the distance between the xt and all the observations, right? After this, you effectively sort it, and then you get the k nearest neighbors. Now we have our k nearest neighbors. That is all well and good, but we need a y hat. We need a prediction. So, you know, we want to find the most, in classification, we want to find the most common class, right? So, and this is where we do that here, the most frequent one. Okay, um, and now we test it out. We make a prediction. This is our test data point, 8, -4, and what do we think it will be? So 8, -4. What's closest? This might not be the easiest one to sort of, you know, eyeball. Blue? I'm gonna guess blue. Yeah, it feels like blue, but we'll let the algorithm will tell us what actually is closer. So that's 0. Now, which class is which? You might ask the question, and that's a very good question. Which one is blue? So let's find out. So 0.5. Okay, yeah. So blue is class 0, and 4 5 is class 1. So 0 1. Let me see if the labels are 0 1. It should be. Let me pull up Y train. Let me just quickly I should have done this before. Sorry, I should have ran it before. Stuck somewhere? What's going on? Anyways, I'll just keep talking while this is happening. There we go. It's coming through. Yes, cool. Yeah. So let's have a look. Why isn't this loading? Computer's a little slow today, isn't it? So I believe that 0 is blue, which kind of makes sense and is consistent with that initial guess that I had. I don't know why Y train is taking a while to load, but that's okay. Everything else is run, so I'll come back to this. I think that's blue though. Cool. Now we. Oh, that's right. It's a NumPy array. I'll explain it. Right. Oh no, there it is. Sorry, yeah. Sorry, ignore that. Yeah. Data. Yeah. So yeah, it's 0 1. Yeah, blue. Yep. I was right. Yep. Okay. Cool. Bye. Go away. Moving along, we tested implementation out a whole bunch of random data, and we want to see what the accuracy is using this k nearest neighbors algorithm. So we're effectively, what are we doing? We're testing this algorithm out using a training and test split, because the problem with the first one was we fed it the entire data set, and you run the risk of overfitting, and you don't have a view of what it's like on the outer sample data, right? So here we're using a pretty standard 75%, 25% training test split. Then we run it through, and the accuracy, as I say, is it's a total number of correct predictions divided by the total number of data. So this function just runs through and gives you the number of observations of where it was correct divided by the total number of observations, the accuracy, right? Okay. Now the question might be posed. This is all well and good, but what is the optimal k? What is the optimal number of neighbors in order to do this, right? Now, there's no easy answer to this. You might have a bit of like, if you're familiar with a particular kind of data, you might have a feel, right? And it could also relate to the complexity of the data set. But hyperparameter tuning is probably the best way, one of the best ways the best way to find out what k, right? What it basically is doing is running a loop here across all the different k's and seeing what the accuracy is. In this case, it's all pretty good. So for me, because they're all pretty good, and let me just check this to see if should be the case, because this seems where did I put it? Awfully good. Services, and then turn on folder. Pretty sure this is the case. Let's have look-sees. Why did my iteration change? Yeah, look, we'll look at, there's probably something I fiddle around here and change, so we'll just look at this one here. But effectively with hyperparameter tuning, you try a whole bunch of different Ks, the number of nearest neighbors, and then you typically pick the one which has the best accuracy on your test data set, right? Now in this case, to me it seems like, 3 is pretty good. After that, I mean, yeah, it might increase, but then actually, sorry, I take that back. It's the other way around. So normally with the simplicity of a model, the higher something is, it can often be, it's more complicated. Now, actually, in this case with K nearest neighbors, the more, in a ways, the more neighbors you have, the less it overfits. Because in the extreme, if K and N is equal to the total number of data, you'd just be the average of the entire data set, or the mode, the most common class of the entire data set. So for me, I'll choose, on the higher end, just for simplicity. Yeah, but all of these accuracy is quite good, and I do stress this is a toy data set, so that is part of the reason why. Let's try it out on MNIST. This is like the ubiquitous handwriting recognition data set that you might have seen. Effectively what it is it is some tabular data, and it is a what's the shape? It is a 28 by 28, whatever that is. You have a data set where each row you can think of it as a new letter, and then each column is one of these pixels. So the 28 times 28, that many number of pixels will be sitting in here. So here it is, and here are all the pixels, 785, right? Pixels, and each one of these will tell you if it's lit up or not. The value here, the value here will tell you how, I guess, lit up or how white the pixel is. Now, of course, we did classic training and test split to prevent overfitting and get a feel of the outer sample data, and this is actually what one of them looks like. So let's apply this. We've done all the hard yards. We've built our K nearest neighbors classifier. Now it's time for us to actually run through and do the prediction. So we go through each of the test data set one by one, and then we run our KNN model and do a prediction, right? And so we try a few different values for K to see what is the best, I suppose. So we're going through runtime, and then finally we print the accuracy. So I mean, this is a really simple model, KNN, and handwriting recognition accuracy 85%. That's pretty good, given how simplistic this model is. I mean, there's at least for this specific data set, there's better trained, more sophisticated models up there that can get high 95% say accuracy, but this is still pretty good, I'd say, for something so simple. Okay, cool. So I will end it there. That was maybe today was a bit shorter, perhaps because we didn't have the maths. But again, tutorials only meant to be an hour anyways. So I thank you all for your time, and I will see you in the consult sessions during the week. Thank you and goodbye.